My name is Radu. I'm gonna try to present this new analysis that we implemented in Infer called Lineage. I'll try to look at the chat in Discord more or less after every slide, so that if you have questions as we go along, I rather catch them early than towards the end. The work here is, so the analysis is mostly implemented by Thibault. He's not here because he couldn't make it, but I'm gonna try to do my best to present what this analysis is about. Now, before telling you what it does and how it works, I want to give you just a tiny bit of background. Both Thibault and me are not in the Infer team, but I rather work for WhatsApp in a team there that is focused on code analysis. And we are mostly interested in looking at Erlang code. That is why one of the things that we contributed to Infer some time ago is the Erlang frontend. So what you see on this slide is the bits that we contributed plus a tiny bit more. For example, the Infer intermediate language was not contributed by us, but it's on the slide nevertheless because it's necessary to put together all the boxes that I want to talk about. And we implemented some analysis on top of Pulse that can be used to find violations of temporal properties in general. That can. Okay, so I'm the next speaker. I cannot hear. Okay. But now I'm going to talk about this box that is here in the lower right part, which is called lineage. What is different between this analysis and the others at a very high level is that it does not output a list of problems with the code, like most of the others do, but it outputs a data structure, basically a graph that can be processed by other tools later on, so it's machine readable. Here's an input-output example of what the analysis does. On the left-hand side, there's some Erlang code, and on the right-hand side is a graphical description of the output of this analysis. I'm gonna guess that not everyone is familiar with Erlang, so I'm gonna spend just a little bit of time saying what the code on the left does. Focusing on lines from 4 to 8. We have two functions definitions, function f and function g. Function g just returns its first argument, and function f calls g, so after executing line 5, a equals x, and after execution line 6, b equals x as well. And at the end we add b with y, so we end up implementing the addition operation in a complicated way. If we look at the graph, because this function adds its two arguments and returns the result, we should see that there is a flow from both argument 0 and argument 1 to the return of function f. And the output is produced using this command line. But we're going to look at this graph in a bit more detail later on. Before that, I just want to tell you what are the high-level characteristics of this analysis. One of the initial design goals that we had in mind was that we tried to be as over-approximating as possible. So our goal was not to reduce false positives, but to reduce false negatives for this particular analysis. And that was one of the reasons that we did not build it on top of Pulse, because Pulse is geared towards under approximations and minimizing false positives. Now this may change in the future, but that was the situation when we started implementing this. The second thing that we had in mind was that we wanted to be really, really fast, because we knew that for some simple examples that we had in mind that we want to handle, we should be able to do it with an analysis that is much simpler than Pulse. So what we ended up with is something that where the analysis time is really negligible. So I have here a comparison with Pulse, but really what is most important is that if you think about compiling Erlang code, converting to intermediate representation, doing the analysis, printing out the graph, it's printed in JSON format. The analysis is actually negligible. Most of the time is spent in the other phases. So it's really quite simple. But we did find that we need to add a little bit of precision to keep track of things that are inside the data structures. So we added a little bit of field sensitivity. So it's not quite the simplest possible thing that you can do, but a little bit smarter. This precision is added, can be added kind of incrementally. You have a parameter, how kind of like the loop unrolling, how much you want, but this is depth in a data structure. So it still works reasonably fast. I mean, it still works really fast with a depth of like 4 or 5, if I remember correctly. Okay, let's see if there's any questions. Not yet. Now, I'm gonna try to tell you how the simple analysis works without this field sensitivity. And then for field sensitivity, we'll see, we might not go in all the details. But for this part, I'll try to pace myself and not go too fast. So if you want me to repeat something or something, just let me know in the chat. So here's the example that you saw in the beginning again, but now we look inside the analysis a little bit to see how it works. And what you see in these boxes in the middle of the slide, these represent the abstract state of the lineage analysis. I forgot to say that the lineage analysis is built on the abstract interpretation framework in Pulse. So it is an abstract interpreter. And what we'll see here is basically what's the abstract domain and what we keep track of in there. Now, something that is slightly unusual for an abstract interpreter is that when you move, so when you execute one instruction, let's say this instruction on line 5, and you go from the state before to the state after, we have this sort of side effect that produces some edges in the output lineage that we compute. So once we finish the abstract interpretation of the procedure, we collect all these edges that were produced while analyzing the procedure, and that's going to be the lineage for that procedure. And it's also what we save as the summary of that procedure, together with a little bit more information that I'm going to talk about in a moment. So what's the abstract state? In the abstract state, we keep track of bindings from variables to the place in the program where we last assigned a value to that variable. So, for example, here this binding x binds to 4 means that it was on line 4 that we gave a value to variable x. In the actual implementation, is not really a number, that a line number. That's for presentation purposes. Here, it's really the node in the control flow graph where this happens. And when we execute, let's execute line 5 here. So on line 5, we assign a value to variable a. So if you look at the state after, the way it differs from the state before is that now you have a binding for a that's saying a was assigned on line 5. And we generate several edges. There's going to be 3 types of edges. There's the edges that kind of copy the values from x to the first argument of g and from y to the second argument of g, so it's copying the arguments. Second type of edge is getting data from the return, the special return variable of g, and putting that into a. And we're going to have kind of a short circuit edge that says directly that x influences a and y influences a. So here on the right hand side we see copying x into first argument is this first edge, and it says it's the x that was last assigned at position 4, and we know that from the abstract state before, that goes into first argument of g. Same thing for y, similar for return. We do the same for line 6, and then oh wait, I forgot to say how the third type of edge gets added. So the one that says that x goes directly and it influences a. So x flows into a directly. That's because the summary of function g contains this piece of information that says that its first argument flows into the return. So because we analyzed g and we got this piece of information, we know to add this shorten here. Now you might wonder, why do we have that? Because here you have a flow from x to the argument 0 of g. Presumably, when we analyzed g, we produced some edges that connect this first argument of g to the return. Then we have this edge that goes from the return to a. So we do record that there's a flow from x to a. But the problem is that if we put together this kind of path that I presented here with what you get from the second set of edges, you're going to get a flow that goes from x directly to b, which is not quite right. So you go from x to argument 0 of g. From the graph that you built when you analyze g, you get from that to the return of g. And here we have from the return of g a flow that goes directly to b. So basically we can confuse the flows from one call to another. That's what people sometimes call context insensitivity. But we can retrieve that by adding this shorthand, these direct edges, these edges that summarize the effect of the procedure we call, and not following edges that go into a different procedure. So instead of going in another procedure and seeing what happens in there, we don't go to different procedures and we look only at these edges that summarize the effect of that procedure. The short version of that is we recover some context sensitivity by doing this. And we see if there's any questions. Not yet. How do we get that red bit that said that argument 0 of g flows into the return? Well, when we analyzed function g, we end up with this green part of the graph. And in that green part of the graph, we do a reachability analysis and we see that there is a path from argument 0 to the return. So to summarize, the way it works is you do abstract interpretation. As a side effect, you produce some edges. To do abstract interpretation, of course, you need the summaries of others, but when you finish, you have these edges and you do a post-processing or reachability on these edges to find out which arguments flow into the returns. And the edges of the current procedures plus the result of this reachability are the summary of the current procedure, which you use when you look at calls to this procedure. So we can see, I'm just going to say that again, but now as sort of pseudocode to try to cover the general case. Okay, I see a question by David that says, how do you handle joins? And that appears on this slide, so I'm going to talk about that right now, well, after I say what's the abstract state. So the general case is the abstract state is a map from variables to set of locations. Now you might wonder why it's the set of location and not just one. And one reason for that is that you have branching. So if you have an if then else, and then you branch, you might have assigned to X in both of the branches. And when you join, what we do is that we keep track of both of those places. So that's pretty much what we do with joins. The other thing that may happen, and should maybe not happen in a function that has only immutable variables, is that you have you assign twice to a variable. And well, let's not talk about that. Because I got slightly confused and I don't think it's important for this. Sorry. So now the abstract state can be viewed as either as a mapping of a variable to a set of locations, or alternatively you can view it as a set of variable location pairs. And then especially if you see it in this alternative view as a set of bindings from variables to locations, then join it, in that view, join is just a union. You take all these bindings together. To handle an assignment, what you do is this: you look up for bindings for the variable on the right hand side that you're processing, and you see where they were last assigned, and you look up for that in the abstract state. For each such binding that you find, you generate an edge that says from that place where you gave a value to X, there's a flow into the Y to which we assign this current location. And once you do that, you update the abstract state by removing all the possible existing bindings for Y and replacing them with one binding that says Y was last assigned at position L. Okay, actually here it's relevant what I wanted to say earlier. Typically there is no binding for Y in the abstract state, because in Erlang you don't write twice to a variable. However, we translate things like list comprehensions into loops. And in that case, there are situations where we do assign several times to a variable. And actually, the main thing to know about this is that we wanted to, although we tested mostly on Erlang, we wanted the analysis to not be very geared towards Erlang, so that we eventually are able to try to analyze other languages as well. And we should be able to do that. It's just that we didn't test it properly. In other languages, you definitely have this situation where you assign two variables several times. Okay. Now, the summary is a pair of the graph that you produce when you analyze each statement, plus this result of the reachability analysis. We call this taint in, taint out result. And it's just a set of argument indices. It's the indices of those arguments that can flow into the return. And the vertices of the graph are these pairs of variable with location or some special vertices that correspond to returns and arguments of a function. We need to know what the summary is if we want to see how the how a call is executed, what's the transfer function for a call. And what we do for that is this. For each of the arguments, we look at all the bindings. We produce edges that basically record that you copy the value from that variable to the argument. And then if in the theta part of the summary of the function that you call, you see that that argument flows into the return, then you also add this squiggly edge that records the flow from xk to y directly. And then because we put flows from into arguments, we also get the flows from the return of f to y and repeat what we did with y. Another question is, how do you merge the graph edges? What we do for graph edges is literally we take the union. We just collect all of them. So it's literally that in the implementation, the representation of this graph is a list of edges, and we collect all those edges in a big list. Then to do the reachability analysis to get this title, we convert that to another representation that is more convenient for reachability analysis. But the actual summary that we save is a list of edges, and we have the other representation just to compute the taint in, taint out. So the reachability analysis that I mentioned, there is only one small tricky thing to mention, which is that it's reachability analysis only on the vertices of the procedure that you just analyzed. You ignore vertices that are in other procedures that you may call. But you do take into account these squiggly arrows that summarize the effect of other procedures. That's the kind of nitpicky thing. The other part that is more important is what about recursive calls? And for that, all I want to say, what we do now is that we assume that all arguments flow into the return, and we don't iterate to find the least fixed point. But that seems to be working okay in general. And because I think we're almost out of time, yes, let's see, there's one more question. Is there a risk to create graph paths that do not make sense? I think the answer to that is no, but I'm not sure exactly what you mean by graph paths that do not make sense. So
Working already. Can you hear us now, Radu?
I see David is typing something. I will try to give a more precise answer if
Can you hear us in the microphone?
I understand better what this is. Okay. Well, I think I'm gonna stop now, and maybe we can move to the Q&A because for the fields, okay, maybe I'll say just one more thing about fields, and that's just the input-output example, and I'm not gonna go into details of how it works in the interest of time. So here is a more complicated example that we handle properly. It says you have this function f that calls swap. Swap is just something, these curly brackets construct a tuple, and this on line 9 you pattern match, and that's how you deconstruct it. You construct another tuple that has the elements swapped. So swap really takes a tuple like a pair in OCaml and swaps the two elements. So you see here what you do is you take the two arguments x and y, you swap them again, and then you take the first element. So what this function f is just returns its first argument. So if you look in the graph here, there should be a path from argument 0 to the return, and that's this path. But there should be no path from argument 1 to the return. And it may look like there are some paths here, but they all go through these round blobs which summarize what other functions do. So there is no path that goes only through nodes of f here. And you only get this more precise version if you add the command line option. And very briefly, the idea is that you have more refined vertices in this function first. Even in this function first, you can see that if you have only one vertex for variable t, then these two vertices will be the same, and you can kind of confuse the paths, and there's going to be a path from argument 1 to the return. But you need to keep separate the two components of the tuple by having these two different nodes in the graph of the two. So that's the main idea. Now, I'm not gonna go in and say how that works, and I'm gonna stop, and maybe we can discuss in Q&A if what David asked and other things. Thank you.
Thank you, Radu. Can you hear us now? I think Boris mentioned that.
Okay, now I'm not sure how we do the Q&A because I cannot hear you.
You can still not hear us. Yeah, maybe it works on the live stream, but not in person. So yeah, but it seems like we have audio on the live stream, but not it doesn't go through to the speaker. But yeah, we can put it in Discord, and then I will read it out, or well, Radu can read it out.
Is it better now, first time, or is it better now, second time, the volume?
Can you hear us now, Radu? I don't think so. I don't know, but it seems like it goes through to the live stream, but not to the speaker themselves.
I think I have an idea of what David means. Yes, so we have the location there to get rid of interference. And I said on one of the slides, I didn't comment on that, that analysis is not path sensitive. But it's actually designed the output so that it can be path sensitive. So the nodes in the graph are in principle something that could be variable x corresponding to this execution path. So the nodes in the output graph can be like that, but they are not because they're not path sensitive. So what can happen is, because we kind of merge all execution paths that reach a certain location, is that we over approximate and you have more paths, which means you lose precision. You can recover that precision by adding path sensitivity, but from what we saw, the main problem was this problem with fields. It was that kind of precision that was more important in practice, and that's why we didn't go after path sensitivity.
Radu, can you hear us in this microphone? Probably no.
So David made a remark in Discord, I'm saying this for people watching this YouTube, that these variable location pairs are what static single assignment form would give you.
Yes. Can you hear us now, Radu? Yes. 1, 2, 3.
Okay, so he should be able to hear us because I can see the icon light up.
Okay. Yeah. I mean, the people in the live stream can hear it, but seems like not our speaker. But then maybe there's an issue on their side.
Let me just try on my phone to make sure that.
Okay. Yeah.
Yes, I listened on YouTube, so my speakers definitely works. If I can turn on the audio on YouTube and then I can kind of hear myself talking.
Okay.
But what I said like 2 minutes ago.
Okay. Well, I think there's no more questions, so maybe we can jump to the next speaker and try to see if it works with them.
So I'm not sure why I cannot hear you. Okay, thank you very much. I'll be around here if you want to talk for a bit more time.